Thanks for everyone showing up for this. The talk today is benefits of GLOST, the greedy launcher of small tasks for many jobs. Oops. So this will interest people who need to run many jobs, as in hundreds, thousands or so. And this is the tool for the type of jobs that you want to run. They can be short and variable duration. You can also do parameter sweeps, such as optimization problems. It's good in advance to know the length of the jobs that you're going to run, and ideally they're approximately in the same sort of order of time. So why do we want to use this? It's convenient as a tool because it takes all these jobs that we have to handle normally individually with the scheduler, at which all of them would involve submitting the job through a script, generating an output file, and then combining results. Using GLOST, you can incorporate all of the input files into one input file and construct underneath. These input files are submitted as an MPI job. So you're running serial jobs typically, probably 95% of the time, and you're doing that by submitting an MPI job. So you need to understand that there's a bit of a learning conceptual step to take when you're dealing with GLOST. And it's convenient because the MPI job inherently will distribute the job throughout the cluster on as many cores as are required and or as many nodes. You could specify the distribution of the resources if you wanted, or you let MPI decide how to spread it across the cluster. And as free cores come up, the job will therefore be started on them as fast as possible. Now, the larger the job gets with an MPI job, there will be some time scheduling the job, so there could be some limits there. But there's all these other benefits which you want to keep in mind that make life a lot easier. So really, you're putting the scheduler to work for you in many ways. So you simply need to, in this case, instead of setting up many input files for all of your serial jobs and organizing them, you can create one input file with each row of this input file will tell the serial job how to start and how to run. So that's basically all of your input files are put into one input file that GLOST will then read and process. And these are independent jobs too. So, and the other implication is the scheduler only needs to start one job. So you're submitting one job and scheduler only needing to start one job. And this is important because the scheduler requires resources of its own to start jobs, and this can create delays and slowdowns. Once the job's started by MPI, that's only one job start for the scheduler. So it's efficient that way. So GLOST is a tool, and it's available in a GitHub repo, and it's very liberal use through it's licensed through GNU GPL 3.0, so you can use it almost anywhere. On the GitHub, you'll find the license. There's a link directly to the full license. If you want to type in the link into your browser and go there right now, this is one of the files that's there. There's also a file called news, which is the location of all the bug fixes, feature enhancements that have occurred up to the current version, which is just 0.3.1 since December 2015, but it seems stable, and I haven't seen any issues running this in my testing. I've done quite a bit last couple of days. There's also a README there. Essentially, I'm trying to get to the point that everything is there. This is the web page for GLOST. So this is, if you want to know where it's coming from, this is it. So the README file will give you the requirements, how to build it, mention the examples, provides some very brief documentation, as well as contact information for the developers. So if you see some way the software could be improved, or you notice a bug or something, then their email address is there. They're in France, and you can just contact them. Great if you let Compute Canada know as well if you did find something. Potentially, there could be you should probably start in Compute Canada. There could be a system issue involved, possibly an installation issue. It's highly unlikely though, because it's a very simple program, which is one of the real beauties of GLOST. Is this thing is not complicated. Right there is mentioned how to check out the source code. You can just clone it to your home directory, go into the directory, run make, and you've got the binaries. Everything that's installed in Compute Canada is right there, works with the default environment. So you could essentially do it yourself, but it's provided as a module on the national clusters. So it's nice to know where things come from. It's nice to download and run make once and see how it builds. Just there's 2 files. It takes less than 5 seconds. But at the end of the day, when you want to use it, you're going to load the module file, as I'm going to show you. Mentioned in the README doc is the section about the documentation, which is extremely important because there really isn't anything else anywhere about it. Like this is the definitive documentation, and I guess it took out my asterisk beside the word documentation for some reason, but there was one there, and it's shown at the bottom of the page. And if you want to pull up any information, all the documentation, you can run the commands at the bottom shown here. So you run the MPI binary, MPI launch with the -H switch, and that will print everything out. The other option is to run man GLOST_launch. Now I notice this isn't on the national systems, but it's on the legacy systems of Sharcnet. So on basically a national system, you need to run the -H switch. There's also another help piece of documentation by running GLOST_filter, which you can check out. So that's where GLOST lives in the repo, and it's all nice and tidy. So how does GLOST work? Again, if you're a developer, you're a C programmer, MPI expert, or just curious how it's doing what it does, because in fact, by understanding how it works, it'll allow you to create the input file easier and to understand what's going on, so you have less questions later. So I would say this page really applies to everybody, and the source of this information was from the previous page, the GLOST launcher -H. So this is verbatim from that page, so you can always reference it. I'm just telling you really where to look for it and find it in the future. You don't have to go back to this presentation. Just run that -H switch. GLOST launch, which is the MPI wrapper, executes in parallel a number of MPI processes -1. And you will notice this when we start running the examples, but once you realize when you're running examples that there's actually a missing MPI process, and you go back to the documentation and you discover that it is well written, that's one of the first things that they say. So I'm pointing it out so that everybody knows. So you're going to specify the number of processes, and it's going to run -1 of them by executing these lines in a task input file, where each one is an independent, let's say, serial job. Okay, so they will start and finish completely independently of their own. There's therefore no dependency on one or the other. This is not the tool. This is not something that GLOST will do if that's what you're looking for. All these serial jobs are completely independent of each other. You just need throughput and an easy way to execute that throughput through the construction of that task file. So the algorithm, again, nice description. You're running GLOST launch on the task file, which creates an MPI job, starts processing all the lines. And the first process is the master that starts, as usual with MPI, and all the others are slaves. So the first is why there's -1, basically because all the slaves are the others, which are doing the work. So the master's in charge of reading the tasks in the input file, and it waits till one of the slaves is free, and then it sends that line to the slave to execute that serial job. When that slave has done the job, it tells the master he's free and ready for another task, as it says, and then the master process passes him another slave. So it just works through the whole input file in this manner, in a perfect form of parallelism. There's no communication between any of these slave processes. Therefore, there's no slowdown associated with any MPI communication efforts. All right, so where is GLOST available? It's on all the National Compute Canada systems because it resides as a module inside CVMFS file system. So it's distributed everywhere. I'll just mention it's also on Sharcnet legacy systems as well, on all of them. So you could use it there. And there is some differences in how you submit a job, since most of the legacy systems are not SLRM. They're done with something known as SQ-sub, but it's not a problem because you're really just submitting an MPI job. So if we get to it, if there's time, I will show you an example how to do that. But the primary goal here is to show you how to submit it on Compute Canada systems through a SLRM script. Compute Canada provides an excellent wiki. It's probably the best information out there that you'll find. And that's what I'm going to focus on. It is so good, it's got a lot of detail that I think it's worth going through it, trying to follow its structure and its naming conventions and whatnot. So if you decide to use it, you might just remember what I was doing and how I was talking about the wiki and recognize all the names and everything else, and you can just zoom through it and put in your stuff and run it, and that make it a lot easier. So the time spent right now should be well worth it. So how do you load GLOST? As mentioned, yeah, you don't need to build it or anything. Just log into one of the clusters. I'm here at Sharcnet, so I'm close to Graham. It's just over at Waterloo. So I'll be logging into that one to run my examples. And module load GLOST. You don't need to specify the version, actually, because it's the only one on there. One of the things, you're going to be submitting the MPI job through a SLRM script. So you want to specify the job runtime, and you want to come as close to that runtime as possible. Overestimating is just going to slow down how quickly a job gets scheduled, because it'll have to reserve resources for a longer period of time. So you don't want to do that. You want to come as close to possible, the real time estimate. So an idealized time estimate is given by this formula, which is taken straight from the Compute Canada wiki page, and it's the time to run one of your serial jobs times how many of them that you've got, of course. But if you're running it on n cores, you've got to divide by n cores. So if you've got 10 jobs and you're running it on 10 cores, it really ends up just taking the time of one serial job, ideally. Well, that's assuming they're all the same. So now you get into a bit of the art of using this software. Like any other software, there's a bit of art attached to it. Now, it's assuming there it's 100% efficient, as mentioned, because it's perfectly parallel. So we're not expecting any slowdown because we're using MPI, which is kind of nice. So getting started, as I mentioned a couple times so far, you've got to submit the job through a Slurm script, which you're probably used to now if you're on the national systems. So all those running jobs, information that you've read off the Compute Canada Wiki, they all apply here. There isn't anything new from that perspective. And because it's an MPI job, we're not going to use MPI run, we're using srun, which is integrated with the Slurm scheduler to start the MPI job. So you've got srun, GLOST, launch, and then your input file. So this will be a line that appears in the Slurm script. So the thing that you've got to worry about, really the only thing here, well, you have the time estimate I mentioned, is constructing, the next big thing is constructing this input file, which is named kind of, it's a little complicated, I suppose. It's unusual, but that's why I want to point it out. List underscore GLOST underscore tasks dot text. So we're going to see that name a lot now, because all the input files are going to be named that in every single example, just so things are going along consistently. All right, so here's this little sample snippet of an input file that you exactly see in list GLOST text. It consists of several lines. So in this case, I've got 5 lines because that's all that fit in the page, but that input file could be 500 or 5,000 or beyond long, depending how many serial jobs you want to run. But each line defines a serial job that you're going to run. So that's pretty easy. So the first job, it's worth noting the and signs and how we construct the task here, which is why it's here. So the first one is assigned an environment variable called 20. And so that job this serial job is really going to be named 20 in the list. And once that variable is set, in this example, which is from the wiki, the real job that runs on the slave is sleep. So I think in the examples of the wiki, they sleep for 360 seconds. So here I put it to 10 to speed things along in the examples. So it sleeps, and then once it successfully completes the sleep, it writes to a file called log underscore 20.txt, which is the third step in that line. So you read it from left to right. You do the first thing, then you do the second thing, which is the sleep. Once that's done, you echo that information, which is 20.hostname, into this log file. So now for that, when that serial job completes, you've got a log file containing output specific to that job. So, well, this GLOST is running in parallel, so actually it's running all of these at the same time, assuming you're running with 5 processors. Now you could be running with 2, in which case it's just going to run 2 at a time, and 2 at a time, 2 at a time, and so forth. But the more cores that you request for the MPI job, the more serial jobs that run simultaneously, the quicker your serial job runs and generates those log output files about what it did or about anything that it did. Now, one of the reasons this is all like this, which is mentioned, is you don't want to overwrite your log file. So in this case, it's from an example where you're writing, all the data is run in the same directory, all the binaries are run in the same directory, and all the output files are generated in the same directory. You don't want to overwrite them. So this is why narg is set to a unique number in each row of the input file. It works its way over, it gets tacked on to the name of the output file, and in fact it's even inside of the output file. So it's a pretty ingenious way to handle this. If you look at it, if you think about it for a couple minutes, then you'll say, wow, this is actually pretty easy, and it's pretty smart too. There's a lot of natural sort of things you want to do all simultaneously, and you just put it in a single line, so it's all in the same place. All right, so I think I've done enough talking on the slides. So I've got some examples. All right, so I can take a second and just show you actually how this was cloned from the repo, because I did mention it. So you can see on this page here. I'll just run that by again. So you clone the output. If you look at the ls command, I don't know if you can see it when I highlight something. These are the source files. There's 2 C files, and you run make on it, and it compiles those. So you end up with the GLOST filter and GLOST launch, which work with the switch. So So the starting point is going back to the last slide I showed with the input file. I'm going to show you one of these commands and just what it does. So I've put it into a script, and this is a demonstration of that narg line from a typical input file, task input file. I'm running it interactively right now. You can just copy paste this at the command line and run one of these commands, because that's really all it is, right? It's a command that you're putting into the input file to be run as a command. So I just ran a command, and there's 2 of them in fact, which are discussed and presented throughout the Compute Canada wiki. The first one is exactly the one I had pasted on the previous page I showed you, and it's run. And if I look at the contents of the what is it generated, there is now indeed this log file with an argument 20, because it was only one of them that I ran, and I can just cat that and see what you get inside is the host name and arg20, exactly what it says there. Now the second command that says run job and subdirectory, that's more complicated, and this is why it's nothing. It's just an extension of the first thing we just ran with a few more and signs mixed into it, because it does more stuff. So again, this is an arg20. In this case, it sets that. Okay, it sets the variable. It's going to create a directory called run, which from my ls command you can see there's run_20 in blue, hopefully, and that is a directory. And then the command goes into that directory. It runs its binary, whatever it, in this case is a sleep command. Once that finishes, it just writes a log file into that directory called log run. Now, why is it called log run and not log_20? Well, it's not necessary, because the directory that the file is in is already named run_20. So if I go into run_20, then it's just the name that it is. That's okay. There's going to be a lot of files called log_run.txt, but they're all in uniquely named subdirectories. So you can choose how you want to organize the output data, if you want to dump it all in the same directory or create subdirectories. These are just the commands how to do both. And I don't want to belabor the point throughout the rest of the examples, but it's partially what's going to happen here. Okay, so let's take the next step and let's run a bunch of these. So I've already got my commands set up in these shell scripts, and they echo out the commands that are inside the little script, so I don't have to type everything in and waste your time on it, and I make typos and things like that. So, all right, so if I run this, what's it doing? It's going to do what it would do if it was run through the srun command, but I'm just doing it interactively. So First thing, I'm going to get rid of all the files from a previous run that are in there. So that's what it did, the rm-f. And then it will load the GLOST module, and then it will run an input file called listglosttask.txt, and that's what it's doing now. It's going to run, there's 12 lines in there, each one sleeping for 10, and I've defined number of processors to be 3, so remember only 2 are actually running. So let's just make this a bit wider so it's easier to see. Right, now they're all in the same line. So you can exactly be 100% confident that even though you put 3, it's going to run 2 slaves. And I've already explained why. And so it works fine. And it's generated files into the current directory. So if you look on the right side of each of those commands, that is the command that the first one to write files into the current directory. And so if I ls, what do you expect are you going to find? Are you going to find run directories with the log.txt or files called log_nr, right? The latter one. So there they are. They're all uniquely named, which is what we've explained is critically important to do, not to overwrite files in the same directory. And so if I look inside each one of those files, it will contain the name of the host name the job ran on and the n argument. So this is progression of steps to getting to actually run the job in the scheduler. So now I think we're ready to do that. So let's go into this would be verbatim example from Compute Canada wiki page. If you go to do it, this is what's going to happen. So I put the commands that you would run in there. So as usual, I'm going to clean off all the contents of the directory that we're in from the previous runs, and then submit the slurm script to the scheduler, which is sbatch run GLOST test.sh, as shown there. It's in the queue now. Alright, so it's running. And you can see that it started to write log files. There's 12 of them in the input file, so I can so it's going to go through each of those. And once it's written them all, it will be done. We can cat the slurm to see where it's at. Okay, so it looks like it's done. Now there's a bit of latency you'll find when these log files are written. So if you're expecting something to be there, it might just not show up for a couple seconds later. In some cases, depending how busy the file system is, and potentially where it's located on the cluster where it got launched. Okay, so that worked. So this is the example generating files to the current directory, and I'll just, as a reminder, again, they contain the host name and the send argument value. Okay, now let's run the example from Compute Canada wiki page where it writes the file into subdirectories of your current directory. So again, it's going to run 12 jobs, and I will submit it. Cleans off previous directories. Those are blown away. Sbatch the slurm input file. We have a job number. we have an alias for SQ, and we're running. So noticing how easy it is to run all these jobs and just 12 at once. So it's all being handled through one job, and just monitoring one job. GLOST is making my life really easy. MPI is distributing the work all over the place, and we're almost done here because each one of these is running sleep for 10 seconds. So total runtime is 60 seconds, ideally, and we can check it. So I just have run.out from previous run, so I'm just not going to re-enter all these commands. Just as a check, you can see from so the sact command, which I've aliased SA, if you look at the top of that terminal, you can see the elapsed time was 1 minute. So indeed, it took about 1 minute to run 12 10-seconds input files using two slaves, so 2 MPI compute processes. And again, if you cat the contents of these log_run text output files, it has the host name and the n-argument value for demonstration purposes. So you can always refer back to this when you go to set your own up to decide what to do. Okay, so that job is done. So let's take a look at the, I really haven't shown you the Slurm input file yet, which I should have. Apologies. So if you look at the Slurm directives there, this used 1 node and 3 tasks per node, so we got 2 processes. I was a little generous on the time estimate of 3 minutes. You know, it's probably could have gotten away with 110, but anyways, and then a gig per. I'm not sure how much. I didn't test how much sleep actually needs to run, but I'm sure I'm wasting a lot of memory there, which is never a good thing. If you're running a lot of, never try to allocate more resources than you actually use, because it'll just take more time in the queue, especially if you're running an MPI job, because it needs to allocate all the resources at once, as I mentioned before. So this Slurm script loads the modules, then it runs srun on GLOST, the input file. So you can find this in the Compute Canada wiki page, that example. So let's make it a little bit more interesting though. So let's try to distribute those onto 3 nodes. So the processes in that example all ran on 1 node. So if you look at this example, I'm just going to change the number of nodes that's used to 3. Previously it was 1, so I've just switched the parameters. Nodes is now 3, and the task per node is 1. So let's try to run GLOST on 3 nodes and see what happens. So again, I got my submit script. Sbatch that Slurm script. It's going to start crunching through the 12 processes, the 12 sleep jobs inside the list. And it's probably started as, okay, so now you can look, if you look at the SQ command, oh, success, it's running on gray 92, 94, and 96, which is interesting. So that's good news, because that's what we requested. catch this in real time. Right. Oh, it's too slow. So I was too slow to catch it in real time, but that's okay. I've already run this, and I've got the output and run.out. So let's just examine what I was going to show you there. Like just a testament how fast this thing goes. So you can't even. I suppose I could increase the sleep time. Okay, so this is just a repeat of what I did. I'd submitted a job before. It's not quite clear. All right, I SQ'd it. That job ran on Gray 64, 65, and 67. So I want to take a look and just sort of prove to myself that those processes are actually distributed to the nodes. So I pdish it and PS, and it lists in sort of a threaded format to show the processes on each node. And if you look around down the left-hand side there, you can see that it's nicely listed: Gray 64, 645, 647, 644. So you ended up with sleep running on one node, sleep running on 645, sleep running on 647. Those are the slaves, and then the master was on 644, which is your srun command. And oh, look at that! It's using 96.7% CPU when it was running. So the GLOST master is very CPU intensive, and of course my sleep commands are pretty much flatlined at 0. You could say they're basically asleep. All right, so I'll just save that. So that just proves that we can put it onto 3 nodes. Let's take a look at this example. Go to the Slurm input file. So it got designated with a 10-second suffix. So this was in fact one of the earlier examples. I think I was going to show you this before. I don't need to run this again. I can just show you the output. So this is an example. I'm going to compare running it for 10 seconds and running it for 100 seconds. So let's just look at the output file for the 10 seconds and see what's happening. So this was run on one node. I should have shown this just before I showed you on all 3 nodes. Anyways, you can see there's an srun command which you can pass the job ID, and it automatically it will process your command on the nodes that the job used. So in this case, it's all on one node, Gray 737. I don't know if people can see this if I'm going too fast. If you're following it, most of it's a repetition of what I do in the previous step, a little bit added on. So right here we are. Job submitted, job is running. You want to see what it's doing because you have no idea. So you can actually you can interrogate these processes on the node by running srun and then the ps command, which everybody knows. And then it shows, oh good, you've got 2 sleep commands in that node running and the master, just what you expected. So GLOST is doing the right thing. And once the job wraps up, you can run the accounting command and see that where it ran, how much memory it used. And this is the input file that generated all the files to the directory. I can cat the Slurm output. And once again, at the end of the day, its written content to the log files in the current directory, which is shown by the ls command. So let's go to 100 seconds. Look at the input file. Aha! So here's something new. If I go back, the point of doing this exercise, if you look at the previous input file, which we just ran on OneNote, each serial job per se was sleeping for 10 seconds. That's all it was. But if you go to this example here, you might wonder, well, one of the things I said back in the beginning, all your GLOST processes ideally have comparably amount the same runtime. And there's a reason for that. So we want to explore that reason so we understand why that this is one of the things and why it would cause you problems, actually. I mean, I'm not just saying that's something you should do and this is what it's for and why not. There's actually a real reason that will impact you severely if you inappropriately choose to use it when you've got some wildly different runtimes. Like in this example, just the first sleep job is going to run for 100 seconds, and then you've got the 10 other jobs. So there's a few things going on here now. When the MPI is running and the slaves are asking for new jobs, one of them is going to, the first process that gets this sleep 100 job is going to be tied up with this job for a long time, for 100 seconds. And then you're wondering, oh, is it going to run the next job? What's going to happen to all the other jobs? Well, that's okay, because this is running in parallel. They're all independent. So the other process, the other slave is going to take up all the work, and it's going to start running. It's going to have to run all the other ones, at least until that 100 finishes. Now there's 12 lines there. There's 12 sleep commands. So the first 100 it's going to just finish before the second last 10 finishes. So it won't outrun. We might get a second process on that first slave that runs. So I can submit this as a job. Okay, now it's starting to go through those, and I think this was on, it's running on one node, and sorry, forgive me to scroll up for a second, just to grab that. All right, so it's running on Gray 284. You can see that, let's look at the output files. It's already up to 27 because it's only taking 10 seconds each. But it's up to 27 and the first sleep 100 is still running. So the first slave is still crunching away at that. And the other slave is working along. And I don't know if I can catch it still doing 100. All right, so process ID 2653 finished, and so the job is now done. All right, so what's the implications of doing that? So I'm going to take a look at a previous job I ran that did the same thing. And if you look at the slurm, well, we can look at the accounting output information. So we can look at the accounting output information, but we can also look at the output in the slurm file to see how long it took. So you can see that the job started 2:57, and then it finished at 2:59. So it took basically twice as long, which makes sense because only basically one core was tied up and the one core was doing all the work sequentially. So it took twice as long as before. So that's a concern. Now, if I take it to the next, if I then again double it to 200 seconds, I run the job. So I won't go through the whole procedure because it's already been done. But if I run this job with 200 seconds again, the one process will be tied up, and then it will continue running as the others are already finished. This 200-second process sits there running until it finishes, while all the other processes in the MPI job are sitting idle. In this case, there's only one other slave. But if you had a large job and one of the job took a lot longer than all of the others, those other ones would be done and this other one would be running. So the job would be wasting a lot of memory potentially and a lot of cores. So this is why, and that could affect your fair share rating and your project allocation and everything else. So you want to be careful that you don't do that. Let's go into this example. I'll just submit it. Let's get it running. And we're going to take a look at the input slurm file. So in this case, I've increased the memory to 50 gigs per CPU, and you're probably wondering what else is new there. Oh, the number of tasks. So suddenly I'm not specifying the number of nodes. I'm not sort of deciding the topology of the distribution, like saying it's on 3 nodes or it's on 1 node or anything like that. I'm going to let MPI use all its power of allocating the resources to find nodes with 50 gigs memory and put them on it. Now, if it can find, it's probably going to look for the small memory nodes, and it can't get 2 of these onto one, so it could get 2 processes on one node, 1 on another, or it could get 3 nodes. So let's see what it did. Okay, so it chose 2 nodes. So yeah, so if you had huge memory serial jobs, you just submit them here. MPI takes care of the distribution of them, no problem. And it's going to try to pack. I believe that it will try to pack them on a single node if it can, and otherwise it's going to distribute them. So that was the point of that example. It's still running. It's going to wrap up in a second. So I'm going to leave that one because I want to get to the... Alright, so... Okay, so in practice, you probably have many serial jobs. So I wanted to demonstrate how to construct an input file, because I've been just giving you these input files that have 12 files, 12 rows in them. So I've created, you can just write yourself a script, like, so what it's going to do is write this essentially. So this, if you cat this gen list, it will erase the original input file, and then it will write all the lines that we're used to seeing so far as the next step in the progression to really get things that we want to do, which are more interesting, which is like parameterization, optimization, explorations, things like that. So you'll have to write yourself a script, generate the input file in practical purposes, and then you can submit your job. You need to wipe out the previous ones. All right, so look, okay, it's cleaned out the directory, it submitted the job, and we're on 3 nodes. It's running 60 processes at once, so really 59. And so it's going to, those are 1,200 serial jobs in the input file. That's why I named the directory that way. And it's going to go through those at a pretty good clip, because these are, again, see, it's already up to 100. It should be done 1,200 pretty quick. In fact, I think it worked out to like a minute again. Everything works out to finishing in a minute. Okay, I'm just going to let that run out. I think it makes the point on that pretty good. And sort of the more interesting one, you might want to run hybrid MPI jobs. So you might want to try to distribute an OpenMP job through MPI instead of a serial job, and that's possible. So I've got this OpenMP job that can create, calculate pi, and it's going to run, it runs according to the Slurm input file. This is the input file to run a hybrid MPI job using GLOST, and there's 2 things to define and to be aware of. So previously we've had CPUs per task set to 1, so it's a serial job, but in this case we want to run 4 cores per OpenMP job, and we're going to have a whole list of those jobs to run and let MPI distribute them. In this case, I'm telling it to use 3 nodes and two processes per node. In fact, that really only means 5 run. And let me just show you the output. So we don't have time to run it, but it's a similar style that we've seen. And to prove it to yourself, prove it to me, and therefore I can prove it to you that it actually works, is that looking in the middle of the screen, if you p-dish onto the 3 nodes that it ran on, 286, 7, and 8, it's run a.out, it's running, and it was at the time, this was last night, 400%, so we have 4 cores running on 286, 4 cores running on 288, and it was running another process on the first master 287, also at 400, so it had three going at the same time. Oh, 4. I'm sorry, there's 5 8.outs, that's correct. And there's the master process, so it's doing the right thing. You've got 4 sets of 4 cores running OpenMP jobs. And when you go to look at how the jobs got done, so when it finished and generated all the log files, you can tell that how many jobs it ran on each node. So I could count them up. There's this kind of curious thing to do. So the one with the master, it actually ran 3. It ran a compute process and it ran the master. So it ran a slave and a master, and then the 2 other nodes just ran slaves. And because only 3 ran on the master node, you had to have one more on one of the slaves, so you got 5. So it works perfectly from my perspective, and hopefully it will work perfectly for you, and I think that's the end of it.